Hello class, this is the pre-lecture video for 3.3. We're talking about the inverse of a matrix. This is a key idea that helps to make solving systems of equations easier and other things as well. I'll connect it to matrices as a transformation that we just touched on a little bit in the last class. So to begin with, the definition of an inverse of a matrix is it's a matrix that you can multiply by another matrix to get the identity matrix. So think of multiplicative inverse. So we think of, if we have a number 2, the multiplicative inverse is 1/2 because it's the number we multiply by 2 to get 1. So here these two are multiplicative inverses of each other. You can multiply the inverse on either side. Key thing, only square matrices have inverses. And the inverse is the same size as the matrix, so they're both square matrices with that are n by n. Yeah, there's that key idea. So this identity, again, just a reminder, it's one's down the diagonal, zero's everywhere else, however large you need it. So in terms of transformations, the inverse matrix, it undoes the transformation that the matrix A does, or your original matrix is. So if multiplying A times a vector x, this is like any point on the plane x, then, and if this transformation that A does rotates everything, any point to the right 90 degrees, and then stretches it out, doesn't like my 9 there, and then doubles the length, then the inverse matrix would rotate it back 90 to the left 90 degrees and shorten it by 2. So that's one way to make sense of the inverse matrices. Another way to make sense of it is in the same way that we have inverse functions. So if I have a function that gives me Celsius in terms of Fahrenheit, where I plug in Fahrenheit and give out Celsius, then the inverse function would give me, I'd plug in Celsius and get out Fahrenheit. So when you're working in contexts, the inverse functions goes back and forth. So in contexts that we've worked before, where we're trying to find the total protein and we're trying to find the servings, that'll give us a certain protein and fat content, then the inverse function would say, well, if these protein and fat content will give you will map to those servings. Okay. The inverse is unique. So if you have an invertible matrix, there's only one matrix. There's a quick proof of that. And the notation we use, it should look similar to the multiplicative inverse notation or function inverse notation. We do that -1 in the exponent. So later on in this video, we'll talk about how in general to find inverse matrices, but there is a straightforward formula for 2x2 matrices. So note you switch these two and you change the sign of these two. So that's the structure here, and then you have to divide by divide each term by a. You multiply AD, so you multiply down. You multiply this way to get AD, and you subtract that multiplication, CB. And then this is a shortcut for finding a 2x2 inverse. Finding inverses is not super easy in general, but we can do it. We'll use row reduction later on to show you how to find one in general. And a key idea here, since not all square matrices have inverses, one quick way is if AD minus BC is 0. That turns out to be the same thing as if you have linearly dependent columns or linearly dependent rows, then you end up getting 0. So this computation is called the determinant of A. The meaning of the determinant of A, and we have a whole section where we'll do determinants later on, but they are introducing the notation right here. In this section, you only need to know the determinant of a 2x2 matrix. But the meaning of the 2x2 matrix, if you think about transformations, recall we had the picture of the cartoon character, and we could do different transformations with it, and the determinant tells us how much the area changes. So if the determinant of the matrix that would transform the blue to the red, then that determinant is going to be like, I don't know, 7 or so, because it's about 7 times larger the area is. And so the inverse function, the inverse matrix, would have to take that red and shrink it down to the blue rectangle, and so that's why you end up so you have to divide by 7 to get the area right. So that's where that determinant comes in. One way to think about that determinant. So determine if the following matrices are invertible, and if they are, compute their inverses. Well, calculating the determinant is a really quick way to figure out if the matrix is invertible. So here you can do 3 minus a negative 2, and that equals 5. So that's not 0, so it is invertible. And then we can apply the formula that we had before. We take the R1 and R3, and notice that we've changed the order of those on that diagonal, and then we changed the sign on that diagonal, and then we divided by our determinant, which was 5. So that's where we get that matrix. In this next one, that's those end up being linear combinations of each other, because you might be able to see if you multiply by a minus 3 halves, then you get the column on the right, or if you multiply by a minus 4 on the first row, you get the second row. And so those are linearly dependent, so the determinant better be 0, and it does turn out to be 0, so that is not invertible. And see, you can go ahead and just do the same computation there. You get a minus 4 for the determinant, and then you just apply that to get the inverse. And you can check, like we could quickly check and make sure. I could put C right here. So this thing, I can write it down there. And then you can do the matrix multiplication. I get a minus 3/4 times 0, 1 times the 1, gets me a 1. Minus 3/4 times 4 will be a minus 3, 1 times 3, those add to 0. 1/4 times 0 is 0, 0 times 1 is 0, add those together. And then I get 1/4 times 4, which is 1, 0 times 3, which is 0. And yep, there it is, the identity matrix. So an inverse is unique, and not only that, we can use that to find solutions of equations. So this is a very popular equation, the kind of equation we end up having to solve a lot with linear systems. So this is equivalent to a system of equations. So B and X are vectors, that's why they're bolded. B here represents a vector of constants, and X represents, this is a vector of variables. So we're trying to find that vector. Wow, that was horrible. There. So we're trying to find what are the values for that in that vector X. Well, we can, if you thought about solving an equation like this for x, where x is just a number, then what would you do? You'd think, oh, I'm going to divide by 2 on both sides. So you don't want to think about dividing with matrices. We have to think about multiplying by the inverse. That also works here, right? We can think of multiplying both sides by a half, and that works out. But we're not really going to think about dividing by a matrix, but we can think about by multiplying by the inverse. So in this equation, I can think about in ax equals b, I can think about multiplying this side by a inverse and then this side by a inverse. And these will just become the identity times x, and this is a inverse b, and so the identity times x is just x, so this is my solution. So if you can find an inverse of a matrix, finding solutions to systems of equations is really easy. And that's what they have you practice here. So you rewrite that system as, notice this is an a, x equals b sort of system now, where x and b are vectors, and x is the variable vector. Again, a, x equals b. And these, I believe, are the same, some of the same matrices we already solved the inverse for. I've already found the inverse for these. Underneath there is a 1, 2, minus 1, 3. And look, it's a 1, 2, minus 1, 3. And this is like C from that page. So what do you do? Well, we're going to multiply by the inverse on both sides, but we know multiplying by the inverse over here times a, you'll just end up with xy on this side. So you multiply the inverse here, and to find the solution, you just have to multiply by that 2 by 2 matrix times 1, 3, and you end up with that. Similarly over here. So some key theorems. If A is invertible, so if A has an inverse, then A inverse is also invertible. So you won't ever end up with an inverse matrix that doesn't have an inverse. And the inverse of the inverse is A. The inverse of A inverse is just A. This one might throw you for a loop. First, if A and B are invertible and by M matrices, then A times B is invertible, and that inverse is B inverse times A inverse. You switch the order. So A times B, two invertible matrices, you multiply together, they have an inverse. They will always have an inverse. And you might think, why do you reverse the order? Well, if I want AB, if I want to multiply something by AB on this side to get the identity matrix, then I have to multiply A inverse by the A. And then, so these, if I write this, then those will become the identity matrix, and then I'll just have B inverse times B, because the identity matrix times either one of those will get itself. And then B inverse times B will be the identity matrix. Well, what if you wanted to multiply something AB on this side to get the inverse? Well, I need to multiply B times B inverse to get rid of it first, and then I'll have the A inverse times A. So matching up so you have the right product at the beginning inside, make sure that works out. If you try doing A, B times A inverse, B inverse, remember, in general, these don't commute, so you can't just switch the order here. So that means that this isn't in general going to be the inverse, and we have to have a matrix that's the same as B inverse times A inverse. And if A is invertible, so is the transpose. This makes sense because if you have a square matrix that's invertible, then the columns are linearly independent. If you take the transpose, then the rows are linearly independent. We know that those are the same thing, so that it will also have an it'll also have an inverse. Oh, and you can find, if you wanted to know the inverse of A transpose, you can just find the inverse of A and then transpose that. There's the proofs of those three things. I'm not going to take time to go through those. We know that if A is invertible, then AX equals B has a unique solution for B. What does this tell us about the reduced row echelon form of A? Well, if there is a unique solution, then we know B is in the span of the columns of A for no matter what B is. So that means A has a pivot in every row. And if AX equals B has a unique solution, then we know A has no free variables. So the columns of A are linearly independent. So A has a pivot in every column. So if A has a pivot in each row and column, then we know A reduces to the identity matrix. This is the really nice situation where we have, if we think of the augmented matrix, we can reduce it to this. Because we're dealing with a square matrix. We're dealing with a square matrix, so we can always reduce it, this side, to, if it's invertible, to the identity matrix. So this is something I'll talk more about in class, but an elementary matrix is a matrix obtained by performing a single row operation. So when we were doing row reduction, let's see, 2, 4, 6. When we're doing row reduction of an augmented matrix, we're doing row operations, but each row operation we could actually do by multiplying the coefficient matrix and the this augmented vector by another matrix. So for example, down here at the bottom, if you want to switch two rows, notice this ABC goes down, this DEF goes up. If you want to switch two rows, then this is the matrix you multiply by. You take the 0, 1, 0, multiply it here, you just get 1D. So that goes up there. 0, 1, 0, come down, you just get your E. 0, 1, 0, come down, you just get your F. So that lines up that one. And then this takes the first row, because my one's going to hit all ABC in the first row, but I'm in the second row here, so it's going to end up ABC there. So each one that we do, each row operation has an elementary matrix associated with it. This multiplies the last row by 5 and it keeps the other rows the same. This combines this multiplies the first row by 4 and adds it to the third row. So that's that kind of operation. This kind just rearranges. So why that's important? Well, we'll talk more about that later. But you can build up. Well, you can build up inverse matrices by multiplying all of the elementary matrices you had to do to row reduce your coefficient matrix. That's why. I know that was fast. It's something that's going to take a lot more explaining, so we'll do it in class. So we're going to use an augmented matrix to find inverse matrices that are beyond a 2x2. It works for a 2x2 also, but we have a shortcut for doing that. So what we're going to do is we're going to take our inverse matrix and we're going to augment it with the identity matrix, not a vector. We're going to do it with an identity matrix. And then we're going to row reduce this side. We're going to row reduce the whole thing, but the focus will be row reducing on this side till it gets to be the identity. And what we end up with over here is the inverse matrix. That's what this represents. So, because all the operations we do on this side, we end up doing with this one in reverse order, and that to undo what we did on this side, you have to do all those. You have to do the reverse operations in the reverse order, and so you're undoing what this one originally does. So let's take a look and see how this goes. So here's the matrix. We want to find the inverse of this. We augment it with the identity matrix, and then we start row reducing. So you multiply this first row by a -4 and add, so that becomes 0. You get a -8 plus 5. We'll get to -3. A -4 times 3 is a -12. You add it to 6, you get a -6. And you've got to do the same thing over here. Don't forget, you have to do the same thing over here. So 1 times a -4, adding to 0, you get a -4. -4 times 0 is 0, -4 times 0 is 0. So you just keep row reducing and making sure you do things to the whole row all the way across. You make the changes, and eventually you're going to get this. If it has an inverse, you'll get 1, 1, 1 down the diagonals and everything else. And this, so that means it's invertible. If we can get the identity over here, it means it's invertible. And this is the inverse matrix. So we could throw it up here and start multiplying to show that they are inverses. So a -2/3, a -4/3, 1, a -2/3, 11/3, a -2, 1, a -2, 1. So I'm not going to do this whole thing, but you can see if I take 1, 2, 3, I get 1 times a -2/3, 2 times a -2/3. So I'm at 2/3 and 4/3, and then I get 3. So I end up with 6/3. Doesn't seem to be enough because I have 3 here. So I have 3 2/3. That only gets me a -2. I think something's wrong here. What am I doing wrong? Or what did they do wrong? I didn't do this work. But there might be a mistake somewhere in here. Oh no, because we need to add to 1, not 0. So we're good. Yeah, so sorry. You get a -2 plus a 3 adds to 1, so you're going to get the 1 there. Sorry, I was thinking we needed a 0 in that spot, so that was throwing me off. Okay. So that's the process for finding inverses. And this process helps you to find out if, as you do the row reduction, if you get a row of zeros, or you get a row where you don't have a pivot, a leading coefficient, or you get a row of zeros on this side, that inverse doesn't exist. So it's got to have, it has to have every column be a pivot column, and every row have a pivot position. So, okay, this is the last slide. Oh, when we say A is an invertible matrix, there's lots of ways for us to know if it's invertible or not. All of these things are equivalent. So A is invertible. That's the same thing as saying A is row equivalent to the n by n identity matrix. So we can reduce row, the reduced row echelon form is the identity matrix. A has n pivot positions because it's an n by n matrix. The equation AX equals 0 has only the trivial solution. And we know that if that has the trivial solution, then we know the columns of A form a linearly independent set. AX equals B has at least one solution for each B in Rn. So, because these would be independent columns, so they will span Rn. So so B is in the span, so we can find a solution. The columns of A span Rn. We just talked about that. There's an n by n matrix that you can multiply C on the multiply by A on the left and get the identity matrix. There's an n by n matrix D that you can multiply on the right to get the identity matrix. And A transpose is an invertible matrix. So if it's easier to find the inverse of A transpose, and that exists, then A has an invertible matrix. All those are the same. So, and we will keep adding to this list because we're going to find more and more things, like the determinant. If the determinant of A is not 0, then we know A is invertible. But yeah, we'll keep finding more and more things that are equivalent to being invertible matrix. And so if we know it's invertible, or if we know any of those things, we know everything else on the list is also true. Okay, thanks.